Okay, we're continuing on here with nuclear chemistry. And last time we talked about several things. We talked about sort of a decay series. We also talked really a lot about first order kinetics. And that really is what all radioactive decay follows, which is that first order kinetics. And there's really kind of two basic equations that go with that. And that's the natural log of A is equal to the natural log of A naught minus KT. This is like your sort of final concentration. This is your initial. This is what is sometimes referred to as the decay constant. And again, they will sometimes use some different symbols for each of these. That's also time. And as we talked about and as we saw last time, we really can use any type of unit in these kinetics equations as long as they're really the same on both sides. So we use grams, I think, in one, milligrams in the other. We did some where there were sort of counts per minute per gram of carbon. So you can really use anything along the way. Again, sometimes they will use like N's for these guys for nucleides. And again, sometimes for the decay constant, they may use lambda as sort of the symbol that is used. With that is the half-life equation, which for first order kinetics is basically this one. The half-life is equal to the natural log of 2. Again, the decay constant here. Usually the decay constant has units of something like 1 over a unit of time. Could be 1 over seconds, 1 over hours, 1 over days, weeks, years, whatever it may be. But typically the units associated with the decay constant is really 1 over some unit of time. As we saw in a number of those examples we did last time, very commonly you might have to use both of these sort of formulas together. A lot of times you may be missing the decay constant but have the half-life. So again, we can use this equation to sort of get the decay constant, and then we can obviously use the top equation for whatever we may be looking for. We also talked about the idea of binding energy or nuclear binding energy. And that is really the mass difference between the nucleons or the particles that make up the nucleus, which is our protons and neutrons, and the mass of that particular isotope. And that little bit of mass difference gets converted into energy through the process of fission. And we talked about a couple different ways you could kind of solve the problem, but they're really all sort of based off of Einstein's equation here, equals mc squared, where that is the mass defect. That is obviously your speed of light, which is a constant of 3 times 10 to the 8 meters per second. Typically, this will be in AMU at the beginning, which means if you use this equation, you'll end up with AMU times meters squared divided by seconds squared. And we talked about using sort of Avogadro's number to the 26 here, which will get you to kilograms. And that will turn your units into kilograms meters squared over seconds squared, which is the same as a joule. So that is one way that you could approach those problems. There's a couple of conversions that we saw, which are basically built off of this equation with the mega electron volts, like 931.5 is equal to 1 AMU. And then you could go from that to joules if you wanted to, using those conversions as well. So you kind of take the conversion route, or you could take the Einstein route to do it. Usually binding energy is given in either joules per nucleon or mega electron volts per nucleon. And again, a nucleon is basically your protons and your neutrons. The stuff that's in the nucleus is basically what those guys are. And that's really like your mass number pretty much. It is also, as we talked about there at the end, a measure of stability. So really the higher binding energy per nucleon that you have, the more stable that sort of isotope is. And obviously opposite of that would be true. The sort of lower the value you have per nucleon, the less stable it is. Any questions on any of that stuff we talked about, I think, last time? All right, so a little bit about nuclear transmutation. One way that you can really sort of create some different isotopes or elements is basically shoot a particle at it. And you can use something like a particle accelerator. It's got a magnetic field and also electrical sort of field. And basically it just gets the particle spinning really, really fast. And then you basically could target it at your target sort of nucleus, if you will. And again, the result of that is a lot how we get some of those man-made elements. You know, they shoot some particles at it, and it basically mutates into something new, and maybe it gets up on the periodic table. You know, like californium, you know, einsteinium, all those type of ones that are at the bottom there. And these are all the ones that you really could find sort of on the bottom row of the periodic table. They're sometimes referred to as the trans uranium elements. And a lot of these guys, again, are pretty much made by that kind of shooting particles at some stable guys. As you can see, maybe some neutrons, maybe some alpha particles, and again, creating some of these sort of man-made-ish type of guys that can be developed. So let's talk a little about nuclear fission and one way that you could do that, which is through sort of transmutation. So nuclear fission, one way that you could kind of kick it off, rather than it sort of happening spontaneously, which it could also obviously happen spontaneously, is as you can see, you got sort of a uranium-235 atom here. You're going to shoot a neutron at it. It's going to become a little upset and turn into a bowling pin here, which means it's going to be unstable. The result of that is it will really split off into two new nucleuses as a result of really that introduction of the neutron to that uranium-235. The result of that is, as well, it will create a bunch of neutrons sort of made as a result of that reaction, and it also will produce a lot of energy. And as we, I think, may saw a similar slide earlier, you know, it's like times 10 to the 13 joules of energy per mole for sort of a fission reaction, versus if you take something like coal and you burn a ton of it, it's like 10 to the 7. The reason that comparison is traditional power plants, right, are like coal powered, right, and they burn coal basically as the energy source. Nuclear power plants do a fission reaction such as this to basically generate the heat of that reaction. We'll talk about that in just a second. But in terms of the products that sort of come out in this sort of fission reaction, it's not always going to be the same two products that will come out. There are certain mass numbers where there's a much higher sort of probability of those guys sort of popping out in these sort of fission reactions with uranium. But again, you might not always get the exact same two guys that come out in terms of the product side. But you typically will get the neutrons coming out and obviously a good amount of energy sort of supplied by that. And that can lead in certain cases to what is sometimes referred to as a nuclear chain reaction. And that's basically a self-sustaining reaction, fission reaction. So if you think about the reaction that we just saw, pretty much you can kick it off with a neutron hitting your uranium. It will split off into those new nucleuses, and a bunch of neutrons are developed, along with obviously energy, which clearly means as sort of the product of that reaction, you're generating the thing that's needed to start it as well. So it could kind of swing back around and kind of kick off that reaction happening again. And there is a sort of minimum amount of mass that's required to basically keep that reaction going, and that's what is sometimes referred to as the critical mass. And in a critical mass situation, again, you're producing these neutrons, which pretty much can continue that process, and it sort of grows exponentially. Obviously, every time it does that, it's releasing a significant amount of energy, not to mention all those products that are probably radioactive themselves, giving off obviously radioactivity along the way. If you have it as sort of a non-critical sort of mass, you know, you could kind of keep that reaction under control without it maybe growing exponentially. That is, I think, like a nuclear sort of bomb-ish. And they have subcritical mass there of our fissionable sort of material. and they have some explosives. So when it hits, it explodes. The wedge completes. You now have the critical mass needed there for this fission reaction to occur. The energy from the explosion also helps out a little bit. And obviously it will kick this sort of chain reaction off, which obviously is not such a great thing to occur. This is also the reaction that basically occurs in a, say, nuclear power plant. And really a nuclear power plant compared to sort of a traditional old-time sort of power plant, there's really kind of no difference in terms of sort of how it operates for the most part. You basically got some water, and basically you heat the water, and the water makes steam. Steam goes out to the turbines, to the generators. You get electricity. They cool down the steam. It sort of circulates back around, and they continue to reheat it, and the lights go on, and all those good things. The main difference between sort of a traditional power plant and a nuclear power plant is really the source of how they heat the water. So in a traditional power plant, they used to just burn coal and obviously use the heat from that reaction to basically boil up the water. In a nuclear power plant, they use a fission reaction, which generates a lot of heat and energy to do that. Obviously, in a nuclear reactor, there's some separation between sort of the fission reaction and sort of the water that's being heated. And in this case, they have typically in there what they used to be referred to as fuel rods. And those are basically like eraser-sized pellets of uranium is basically in those. And that serves as obviously the fuel for the fission reaction. Has some water in there and sort of an enclosed container, which will heat this sort of pipe, which is going to heat the bigger water, causing obviously the steam that goes out to the turbines and the generators. Now, a lot of times in terms of safety, there's a number of safety things that are obviously involved in this sort of process. One very important one is usually there are what are referred to as control rods, and control rods are things that have something like cadmium, which is a good neutron absorber. Then why would a neutron absorber be pretty good in this deal? Yeah. Oh, yeah, that would be a good answer, I suppose. Yeah, so basically it is basically the neutrons that start the reaction, right? Keep the reaction going. So if you got these sort of control rods, which basically take some of those neutrons out of the reaction, it's going to kind of keep the reaction under control. Clearly, they also usually will do a non-critical sort of mass along the way to keep it hopefully under control. Unless they take out too many of the control rods at once, and then it's not going to be under control, which I think was sort of what happened there in Chernobyl, is they sort of removed a little bit too many of those at once, and a safety test that didn't go so well. But they do that to keep that under control. Usually these guys also have obviously a lot of shielding, big cement guys around those reactors. Ours is out there right in San Onofre, although they're not working, I don't think, anymore. Are shutting them down. But right there, the big two cement towers, also located usually by a very big body of water, so they could use it to cool down the steam, right, and have that whole process to go around like that. They happen not to be located near a big body of water, like say in Arizona. They have really big cooling towers full of like water that they kind of use in that sort of process. There's one off there, Palo Verde, I think off the 10. As you drive out to Arizona, there's a power plant over there. And so there's good and bad, obviously, with this. Some of the good is technically it's a little bit cleaner in terms of energy and burning rather than burning coal, which gives a lot of pollutants, but it's also not so great because there's a lot of side products, right, of this reaction, which hang around for a very, very long period of time. So there's kind of good and bad, really of both. What do you do with all that sort of waste products, if you will? Sometimes referred to as spent fuel. Spent fuel is basically all the byproducts that are still super radioactive for a very long period of time. These things have half-lives of like thousands and thousands of years, which means where do you put it? Who watches it? Who controls over it? And obviously burning coal is not so good as well. It gives off some pollutants and stuff like that. So I think they've started using it, but many years ago they built the big thing in Nevada, right, to kind of house a lot of the nuclear stuff. And for many years, people are like, how are you going to get it there? Not through my town. Don't send that stuff through my town. But I think they've started to use it. Hence why the neon lights stay so bright there when you're in Vegas. So this is some of these, what is again referred to as spent fuel. And again, as you can see, this is really the time and years that you got to store some of these things. And yeah, we're not going to be around for that long period of time for those things to sort of die down. So for many, many years, because they really didn't have a place for it, a lot of the nuclear power plants would actually just kind of hold all that stuff right there on their site. A lot of them are shutting down because to kind of bring them up to code and stuff like that, it's like not cost effective and stuff like that. So I think both at San Onofre really aren't working anymore. They sort of shut them down, and a lot of them across the country are sort of shutting down. What's that? Yeah, to kind of bring them up to sort of code. It'd be not that they're not safe, but under new sort of regulations and stuff like that. Yeah, and stuff like that. So I think a lot of the sort of energy companies decided it's maybe not worth it to reinvest sort of in it. So that is fission. Let's talk a little bit about fusion, which is a little bit different of a reaction. So in a nuclear fusion reaction, we actually take two smaller nuclei together and fuse them together. This happens at super high temperatures, like your vacation on the sun type temperatures. That sort of high temperatures is where that sort of occurs. And as you can see here, we get the two smaller guys, again, making sort of that larger isotope there. The old movies where they got the guy that made cold fusion, right? That's what they always try to get, that scientist guy. Now let's just finish up talking about radioisotopes in medicine, as we might have mentioned the other day. Clearly, if you're using something for medicine, you do want something with a much smaller half-life. Otherwise, again, that follow-up appointment is going to be a very long period of time. But here's some examples of some stuff that's used and what they're used for, like sodium-24, iodine there, sodium, a blood tracer, brain imaging. The nice thing about isotopes is pretty much in the body, even if they're radioactive, they pretty much perform the same chemistry as the non-radioactive version. So it is basically just like labeling things, right, where you could follow the radioactivity and see where things go. And in a scan, they obviously will highlight in terms of the radioactivity and show up. They also, for a lot of years, and still do, I think, would put some radioactive seeds in tumors and stuff like that to try to shrink them, and obviously they would have to be taken out at certain points. So again, here's an example, sort of a bone scan with technetium 99. And again, you can see hours in terms of sort of half-lives, which means, you know, within a day or so, it's not so bad or so radioactive. Now, when you are working with radioactivity, you usually will grab one of these guys, which is a Geiger counter, and it's really a wand that kind of makes a beeping sound, and you go around and it beeps. You hopefully point at yourself it doesn't beep so much, right, after you're done doing it. You should always check your shoes, because that's where people step on things and take it home with you. But we do use the Geiger counter, and again, it's one way to sort of measure it. If you do a lot of work with radioactivity, they used to make you wear like a ring and like a little badge, and years ago it had like film in it, and they would develop it after so many times of use and go, well, maybe you should take a little vacation and stuff like that. And what some people would sometimes do, not thinking about it, is they would leave their lab coat with their badge on it right next to their experiment, sitting there baking all day, and they're not really in it. In case you wanted a vacation, you know, you maybe would do those things, but they will do those things. And when you clean up, you should always check with the Geiger counter. If I hold the Geiger counter up in the air, will it make a noise? It will. There's background radiation, which is the common thing you hear when somebody's holding a Geiger counter. Don't worry about it. It's just background radiation. That's super loud beep, beep, beep. It's nothing to worry about. It's all right. Yeah, there's background radiation. So you lift it up, you will hear it beep. Hopefully not loud, but it'll be a small little sort of beep. Speaking of that, there's a couple of ways that we look at sort of exposure time, and one's a RAD, which is a radiation absorbed dose, and one is a REM, which is sort of the equivalent for man. And it really does depend on the sort of type of emitter. So as I mentioned at the beginning of this sort of chapter, if you ever find yourself working with radioactivity, you should always investigate yourself, make sure you understand what type of emitter it is. Again, some things don't penetrate as far as other types. Alpha particles don't go as far into the tissue as, say, gamma rays, which go very far. And also you need a lot of sort of protection when you're doing that. So that's why they basically take the rad and times it by the factor, and you can see the alpha factor is a lot higher of a number because it doesn't penetrate as far. So, you're not in so much trouble if you get exposed to a lot of that. Try not to get exposed to most things. Obviously, time as well, staying away from it, not standing over it if you're doing experiments. Sometimes that's easier said than done. These are some places where we could get some exposure. Obviously, cosmic rays, ground and surroundings, medical, x-rays, air travel. If you're near a fallout and weapons tester, I guess you get a little bit more, and nuclear waste as well. So, we do pick up some of this background radiation in our everyday life. And that's strawberries. Good deal. That is this chapter. Yeah. Any questions on that there? Okay. So we're going to then roll to the next chapter. Just give me 1 second to find it. That should also be the last chapter for the exam, which is next Thursday. Yeah. So it's nuclear chemistry and electrochemistry. Yeah, sounds like a good mixture, I think. All right, so in this chapter, we're going to talk about transition metals, and we're going to talk about coordination compounds and complex ions. We're going to start with sort of transition metals, as a majority of complex ions pretty much have a transition metal in the middle. So we're going to talk a little bit about some things that hopefully will be some review of transition metals, some of the properties of them, and obviously some characteristics of them, and then we'll get into really the heart of the chapter, which is about coordination compounds and complex ions. So let's start with transition metals, and before we start with that, let's start with the idea of effective nuclear charge, and that's Z effective. And that really is the sort of positive charge that the electrons feel from the nucleus. And the idea here is not all electrons will feel pretty much the same positive charge that other electrons feel. And there is an attraction between electrons in an atom and the nucleus, because nucleus is positively charged, electrons are negatively charged. So that is that opposites attract. And this also explains why in certain cases, only a certain type of electron is involved in something like bonding, right? And those are the valence electrons, those outermost electrons, rather than the core electrons. So for example, we just look at a pretty simple, straightforward one, which is our friend lithium. That is 1s2, 2s1 in terms of its electron configuration. Lithium is not a transition metal, by the way, but it is just has 3 electrons. It basically means that it has 1 valence electron, which is this guy, right? And it has basically 2 lower energy electrons closer to the nucleus, which are sometimes referred to as core electrons, right? And those are obviously not the ones involved in bonding because they are pretty much close to the nucleus. So the idea of effective nuclear charge is you got a nucleus like lithium there, just got a nice +3 charge. You got a couple of electrons in the first energy level, right? That n equals 1, that principal quantum number. And you got 1 electron in a higher energy, and we'll just kind of draw them all next to each other like that. So really the sort of core electrons here, they are pretty much right on top of the nucleus. So they're going to feel that full brunt of that +3 charge, which means they're going to be held pretty tightly. In terms of electrostatic attraction, in terms of charges, the higher the number of charge, the stronger the attraction is. So if you have something that's like a +3 and a -3 coming together, that's going to be held tighter than something that is like a +1 and -1 that comes together. So as the charges increase, so there's that attraction force that holds it together. When it comes to this valence electron here, it is actually experiencing what is sometimes referred to as shielding. So this valence electron here is experiencing shielding from the lower energy electrons. They're sort of in its path, if you will, to the nucleus. And so because it's sort of in its way, you know, kind of like when you go to the movie theater, and years ago you could just pick your own seat, I think, right? And you roll in there and you sit down, you got a nice seat right in the middle, nobody around you. And like right before the movie starts, somebody comes in front of you with a big giant cowboy hat, shielding half of the screen, right? And you cannot see it. So it's a similar sort of effect for this electron. So instead of feeling that full positive charge, you could actually calculate the Z effective as the atomic number minus really the number of core electrons. So in the case of lithium, we have basically a +3, and if you want, you can add its -2 for its 2 electrons that are there. So effectively, that outer electron is actually only feeling a +1 sort of attraction to the nucleus, which means, again, it's not going to be held as tightly. And that is why when lithium loses an electron, that is the one that takes a hike, because it is not held as tightly, easier to remove, less ionization energy to get that guy to come off. So in terms of Z effective, the typical sort of pattern that we see is as you go kind of right and up on the periodic table there, the Z effective does increase. And this is what we're looking here. This is period 3 on the periodic table, going across the periodic table in period 3. And we do see that the Z effective increases. The result of that is we also see that the atomic radius decreases as you go to the right. That's also because as you go to the right, you are putting in more protons, bigger positive charge is going to bring everybody in closer to each other because of that larger positive charge. So that Z effective increases as you go to the right, sort of decreases as you go down. And we also see in terms of size, as you can see, atomic size sort of decreases, gets much smaller on this side, obviously much larger heading onto that side. This also plays a lot of roles into what we know happens with these type of elements. Metals, right, are typically ones that will give away their electrons, right? And non-metals are typically the ones that will accept the electrons. So these are our transition metals. Case you forgot right there, between group number 2 and group number 3, it is these guys right here, all the way down. In addition, on the bottom, these 2 rows technically go right about there, and they're sometimes referred to as the inner transition metals, although we do not use them too much here in coordination chemistry. They are, as we were just in the last chapter, where a lot of those radioactive elements are on the bottom. And here you go again. Speaking of transition metals, they basically start in terms of electron configuration in what is referred to as the D block, right? And the first 2 columns or groups is the S block. This is the P block going this way. And this is our F block in terms of electron configuration going that way. That's because in terms of S orbitals, you can put a maximum of 2 electrons in it. That is like 1 and 2. P subshell, since there's 3 different P orbitals, you can put 2 electrons in each. That is 6, so that is 4, 5, and 6. D, you could put 10 electrons in that subshell, 3, 4, 5, 6, 7, 8, 9, and 10. And I won't count it, but 14 coming across that way on the F. You could actually count electron configuration from the periodic table by using the period number, right? The period number basically equals the quantum number, the principal quantum number. That's like equal to the N number, basically, these guys. There are a few things that you should be aware of. The d orbitals don't first start to appear until the 3rd energy level, right? So even though this guy right here is on the 4th period, this is actually 3D, and that would be 4D, 5D, and 6D. And Fs actually don't start to the 4th energy level, and that's actually 2 behind where it should go in the periodic table, which is period number 6. That's 4F, and below it would be 5F in terms of electron configuration. So transition metals do show very similarities, obviously within a period, as well as a group, and most things on the periodic table, right, are sort of related to each other based on sort of where they're at. Now, when they do form ionic compounds, they often can have more than one oxidation state. That's also why when you name something, right, with a transition metal in it, we usually use a Roman numeral to indicate the charge that's on that guy when we're naming something that's an ionic compound that has a transition metal in it. Cations are often complex ion species where we have that sort of transition metal in the middle, and we have a lot of ligands that are attached to it. And basically, we have this metal ion in the middle that's positively charged, and attached to it are a bunch of ligands. Now, ligands are really Lewis bases, and you will tell me that Lewis bases are things that do what? Close. Lewis, though, is about electrons when we talked about acid and bases, and Lewis has to do with electrons actually being donated, is what a Lewis base is. They will donate a pair of electrons. And they will donate typically a pair of electrons to something that is a Lewis acid, which is something that will accept a pair of electrons. And that is a little bit different than for the Bronsted-Lowry definition of acid and bases, where the base actually accepts a proton in H+, and the acid donates H+. So with the Lewis, it's sort of opposite in terms of donating and accepting, and it's about electron pairs. In order for something to sort of donate electron pairs, it needs to have a pair of electrons or some non-bonding electrons to donate. And usually if it does, it usually needs to be kind of like a polar molecule, like our friend water is actually a Lewis base. It has these non-bonding electron pairs on the oxygen, and it is polar, which makes it a pretty good Lewis base. Something like ammonia as well is a Lewis base. It is polar, and on that electronegative nitrogen there, it's got those non-bonding electrons. Other things that are really good Lewis bases are things that have negative charges, because in order for them to have negative charges, they had to gain electrons, which means they have electrons to give. So things like chloride, Cl- is a good Lewis base. The positive metal in the middle is a good Lewis acid, because in order for you to be positive, what had to happen to your electrons? You had to lose them, right? Which means you're electron deficient. And if you have a pretty good positive charge, like a +2, +3, +4, you're fairly electron deficient, which means you're good to go to accept the electrons that these Lewis bases want to give you. So that's why we look at, really, as we'll talk about in this chapter, sort of complex ion formation, more like a Lewis acid base situation that's happening, where we're sort of donating and accepting electron pairs. Any questions on that there? And here's an example of that. Here in the middle, we have cobalt with actually a +3 charge. And again, the ammonia here is a good ligand. And in this case, it actually can handle 6 sort of those ammonia guys coming in. And each of those ammonias will be attached to the nitrogen there. So the nitrogen in each of those ammonias is the one place where it will give away those electron pairs. And that attachment point happens. And we will make this complex ion here, the CONH3 6 3+, which by the end of this chapter, you will properly know how to name that. You will probably say that that is something like hexamine cobalt 3 ion. Yeah, there we go. So rather than like that thing, whatever that thing is called, is what we're talking about. When we used to do a lot of qualitative analysis experiments, people would always come up and go, like this thing, like whatever this is called. And it was all these complex ions that would be formed. All right, so let's talk a little bit about ionic compounds and transition metals. So most compounds have some type of color that occurs because of the transition metal ion in the complex ion, and it can absorb light. And as I think we maybe talked about in earlier experiments and stuff like that, right? The color that we see in terms of the solution is the complementary color, right, to the wavelength of light that is being absorbed. And that's why when we do like our spec 20s or whatever we use, we set it to the complementary color rather than like if we have a solution that's red in color, we don't set the wavelength to red, we set it to its complementary color because that is the wavelength of light that's being absorbed. Many compounds that have transition metals are paramagnetic. Paramagnetic means, yes, it means unpaired electrons they have. Yes, that's what that means. So they have some unpaired electrons is what paramagnetic means. Diamagnetic means paired up electrons, yeah, opposite spins. We have our spin quantum number of ms, yes. When the electrons go in, no more than 2 electrons per orbital, right? That is Pauli's exclusion rule, and that is because no 2 electrons could have the same 4 quantum numbers. N, L, M sub L, and M sub S are the 4 quantum numbers. Perhaps you learned that in 200A. Yes. And this guy going in the upwards direction, or not, plus a half, minus a half here. And again, that is typically what is referred to as being paired when you put them obviously in opposite spins. Unpaired electrons are paramagnetic, so upward type of thing. Hund's rule, we maximize the parallel spins, right? In a situation where we have multiple orbitals in a subshell, we go one at a time and then come back and pair them up when we do that. All right, that was a fun 200A throwback. All right. So let's continue our throwback lesson of electron configuration, yes? Just to make sure everybody's on the same page here. We write electron configuration, obviously, in terms of filling, how the electrons go into the atom. They do go into the atom, right, lowest energy level first, and continue to fill until, obviously, all the electrons are distributed. There's a certain order at which they go in. And you can make a little key for yourself if you need to and don't want to count off the periodic table. First energy level, there's s orbitals. Second energy level, there's p. Third energy level, there's d. And fourth energy level, there are f's. And you basically can just fill in the numbers underneath it. And that'll be 4D, 5D, 6D, and 4F, 5F. And maybe seeing something like this, this is the order of filling as they come through here. And the main difference that always messes people up is right about there. The s orbitals, specifically the 4s orbital, is actually lower in energy than the 3D orbital. So they actually do get the electrons first, followed by the electrons going into the 3D orbital where we will be with our transition metals. Reminder, S, you could hold 2 electrons maximum, right? P subshell 6, D subshell 10, F subshell 14 electrons maximum. And when electrons go in, they do fill up the S first, then they start filling up the D orbitals. And it's actually at that point in time that there's a switch in terms of the energy level. Once you start populating the D orbitals, the 4s orbitals actually become higher in energy than the 3D. And that plays a very big role in terms of transition metals, in terms of what electrons they lose when they become positively charged. Transition metals typically will always lose the s electrons first because they end up being higher in energy. And then if they need more, then they dip into basically the d orbitals to take out whatever left that they need. This is really important because later on when we talk about complex ions, you need to be able to figure out how many electrons a transition metal has. That is noble gas configuration, right? That's argon's configuration. We did something like sodium, which is just not too long of a one. 1s2, 2s2, 2p6, 3s1. Up here is 10 electrons by counting the top number. That is the same electron configuration as neon, so that is a noble gas, and then you continue on with it. It always has to be the noble gas that comes right before whatever one you're writing the electron configuration for. There are several exceptions to normal electron configuration if you follow this filling order that exists. Most people focus in on chromium, which is 24, and copper, which is 29. And it's been found experimentally that it is much more stable with one extra electron up in the d orbital, actually for both of them, one less electron in the s orbital. And for the chromium, that would make sure that all d orbitals have one unpaired electron heading upward. That actually would maximize a lot of the parallel spin. And for copper, that will kind of pair off everybody there in the copper subshell. Now, you may also know, or not, that underneath chromium and copper on the periodic table kind of go over and to the right and to the left. There's a lot more exceptions to normal electron configuration. Things like silver is an exception. Things like PD is an exception. For example, PD has like no electrons in its s orbital. They've all been sort of promoted up to the d orbital. So there's a lot of exceptions in electron configuration in that transition metal region. Most of the time, though, we just focus on a lot of times chromium and copper as the two that we see. Now, speaking of when these transition metals do form ions, as I mentioned before, they will get rid of those d orbitals. There's s orbitals first, and then into the d orbitals. So if we look at Ti, which this is electron configuration with no charge, 4s2, 3d2, with a +3 charge means this guy has lost 3 electrons. And again, the first 2 electrons it will lose will be the 4s, because after we put them into the d, it is actually higher in energy. Then it will go and grab that 3rd electron out of the d orbital there, and we will end up with argon 3d1. Any questions on that there? All right, why don't you try iron 3 and write the configuration for nickel with a +4 charge. Iron is number 26 on the periodic table, and nickel is 28. Okay, let's take a look. So iron is 26. So iron with no charge would be argon 4s2, and then you could literally count from SC as 1, 2, 3, 4, 5, 6, 3d6. Yep. So +3 means it has lost 3 electrons. Once again, it's going to always lose the s first. That is 2 electrons. Then it will lose one of those, which would leave us argon 3d5 in this case. Yeah. Looking at nickel, nickel with no charge, going to be argon 4s2, and that is 1, 2, 3, 4, 5, 6, 7, 8, 3d8 here. Once again, here it's got a +4, which means it has lost 4 electrons. Going to dump the s electrons first. Then we'll take out 2 of those electrons, and that is going to leave us argon, or just argon 3d6 in this case. Any questions on how to write electron configuration? So again, later on this chapter, we're going to do some things, and part of that is you'll need to figure out again how many sort of unpaired electrons is a common question that occurs, and that means that you do need to know how many d electrons these transition metals have. All right, so let's finish talking about some of these other sort of properties of our first row transition metals. In terms of oxidation states, they can have a wide variety of oxidation states. You can kind of see it builds as you head towards the middle there, with Mn having a lot of different oxidation states, anywhere from +7 to +2, depending on the situation. It does sort of drop back down, coming out the other way. A vast majority, though, of our transition metals finds itself in that kind of +2, +3 sort of area. But then again, it can be some other ones, depending on what it is it's attached to. That leads us to ionization energy, and a reminder that ionization energy is the energy required to remove an electron from the gas phase of an atom. And when we remove electrons, that essentially is the formation of a cation, right, which is positively charged. And that is usually what we sort of think about in terms of ionization energy. The general trend for ionization energy overall, our first ionization energy, is it increases as you go up and to the right and decreases as you go down and to the left. Electrons actually do come off one at a time, so they all just don't drop off at once. They do have kind of a stepwise fashion. So for example, if we looked at magnesium, which we got going on down there, I think. First thing that would happen is magnesium there would drop an electron and become +1 charge. This would be the first ionization energy, and that's the energy required to move that first electron. Next that will happen is the magnesium with a +1 charge will then drop a second electron there. And that is what is referred to as the second ionization energy. Maybe it then loses a third electron, which would be the third ionization energy. Obviously, you can continue on as many electrons as you like there. Is it easier to remove the first electron or like the second or third electron? Which one's easier to remove? The one that's actually easier to remove is actually the first electron is actually the easiest to remove. The element is neutral, right? And when you lose an electron, what happens then to the size of the ion? Does it get larger or smaller? It gets smaller, right? It lost electrons, so it condenses down, it loses some of its electron cloud. That also moves any remaining electrons now closer to the nucleus, right? And closer to that positive charge. It's going to hold on to it a lot tighter. So it gets progressively harder, right? You drop that second electron, now everybody condenses a little bit further, and they're being held a lot tighter. And we see that if we look at, say, something like magnesium, the first ionization energy to remove that first electron, about 735. You kind of double it when you take off that second one, a little bit harder, but then there's a pretty good jump there as you try to pull off that third electron. That's about a 7-fold jump in terms of energy that is necessary to try to rip off of the third electron. And that is because if we look at the electron configuration for magnesium, 1s2, 2s2, 2p6, 3s2, these two electrons here, right, are its valence electrons. These guys are now the core electrons. So after I successfully remove my first one, then my second one, I am now into those core electrons, which have now moved super close to the nucleus, right? And it pretty much doesn't happen. That's why we know magnesium is a +2 charge, because it's able to rip off those valence electrons, but it takes way too much energy to try to rip out that core electron out of that much closer spot to the nucleus. That's why something like magnesium is a +2 charge. Also why something like sodium is a +1 charge, right? First electron about 495, then you need about 10-fold the energy if you want to try to rip off its core electron. Again, doesn't usually happen under normal conditions. That's why there are certain things on the periodic table that have fixed charges, because those valence electrons, again, are easier to remove. It does get progressively harder as you go through it. So the general trend that we see for ionization energy, for first ionization energy, is it does increase as you go to the right, decrease as you go down. We also see the trend that as you go from the first ionization energy to the second to the third to however many it may be, the ionization energy increases. It gets much, much harder to continuously try to remove electrons from an atom. Any questions on that there? All right, so here's a bunch of information in regard to our transition metals, which you clearly should know everything on here, and probably not. But we talked about some of this. We talked about electron configuration. We talked about the size decreasing. That's our ionization energy increasing as you go from the first to the second to the third. Common oxidation states, again, 2s and 3s, and some others through there. We also see density sort of increases generally as you go to the right, again, across the period there with our transition metals. That is our graph of first ionization energy versus third. And again, you can see it's much higher on the third energy level, or the third ionization energy to remove those electrons. Here's one in case you didn't like the first picture that includes the second. Again, higher to the second, and then obviously higher to the third. Now, electron affinity is another thing that we oftentimes will sometimes look at. And electron affinity is the energy change that occurs when an atom basically gains an electron. So when somebody gains an electron, that's pretty much an anion formation, right? It becomes negatively charged. Electron affinity increases as you go this way and decreases as you go that way. It is not a perfect sort of pattern, but that is the general sort of pattern for electron affinity. And we can see even in group 7, it doesn't really follow that perfectly. Here are the electron affinity for our group 7. It does increase as you go up, but then it kind of comes back down a little bit as we get to the top there. So it's not a perfect trend, but that is the general trend overall. This should not be confused with everybody's other favorite thing, which is electronegativity. Yes. Electronegativity is the ability of an atom to bring electrons towards itself. Also on the periodic table, increases as you go this way, right? Decreases as you go this way. Most electronegative element is? It is fluorine. That's a much better answer than I had earlier today. I was very silent earlier today when I asked that question. So yeah, fluorine is the most electronegative one. It pretty much is as far up and to the right as you could get, except for the noble gases. Noble gases are chemically inert. They're perfectly happy. They're not looking for electrons. They have electronegativity values of 0, right? They really don't want any more electrons. Pretty much everybody wants to be like them. That's what the whole purpose of bonding is for everybody to end up with the same electron configuration as the noble gases. So, a lot of these trends that we just sort of talked about, again, reemphasizes what we sort of should know. Again, as you go up and to the right, our nonmetals are typically the ones that want to gain electrons, bring electrons towards themselves, not looking to remove electrons. And obviously, metals are pretty much the opposite of that. Metals are pretty much about, go ahead, take my electrons. I'm not really interested in hanging on to them, nor do I really want to bring electrons towards myself. And that's why sort of in our complex ion situation, our transition metals are really that sort of electron deficient, looking to kind of gain those electrons or willing to gain those electrons because they pretty much are deficient of those electrons. All right. This is relative reducing abilities of the first row transition metals. And as we increase on this particular list, and this is our first guy in the transition metal period, and that's heading, across the periodic table going in this direction here. We actually see reducing ability. That's a much better reducing agent, for example. And that reducing agent means that it will be oxidized, right? Now you may say to yourself, that's a very positive number, shouldn't it be reduced? And the difference is these reactions are reduction reactions or oxidation reactions. These are all oxidation reactions. Electrons are on the right-hand side, yeah? So they're being given off. So these are like standard oxidation potential, perhaps. And that means that if I wanted to compare it to what we were talking about with electrochemistry, and I wanted the reduction reaction, I would reverse all those reactions. And if I reversed all those reactions and turned them into an SRP, I would change the sign of all these guys, right? Which would make all these guys negative. Then makes this guy positive at the end. And that means that this guy down here would be the guy that gets reduced, right? A much better oxidizing agent on that bottom. So if you flip those around and change the E, it is the same thing that we talked about when we talked about anode cathode. The more positive guy would be the guy that gets reduced. And obviously the least positive guy, which actually would be the negative guy at the top, would be the guy that gets oxidized. Again, it's just backwards on this list because it's the oxidation, not the reduction reaction. All right. This is what the first row transition metals look like in case you need to pick them out of a lineup or something. That is our Penny and Abe there. This used to be very helpful when we did general unknowns, but we don't do those anymore, so you don't have to worry too much about these. But some of these transition metals, which are in a lot of those, obviously, qualitative analysis experiments that we did, they do form some similar type of colors depending on what they're attached to. So sometimes you could almost kind of figure out maybe what was in your unknown based on some of the colors that you would see, and obviously different oxidation numbers. But we don't do that anymore, so when we just slide through those slides. Yeah. All right, now that we have sort of a nice background about transition metals, what's related to what we were going to be really talking about for the rest of this chapter, and really the heart of this chapter, which is coordination compounds. So let's talk about a coordination compound. A coordination compound will consist of basically two things. It will consist of that complex ion, that obviously has a lot of cases, transition metal in the middle, those ligands that are attached. And because it is a complex ion, it's an ion, it has a charge, and it will consist of a counter ion. And as we will talk about, your complex ion could be either positive or negative. And that also means that you could have either a positive or negative counter ion depending on the charge of your complex ion. You could think of coordination compounds sort of like an ionic compound. And when we put an ionic compound together, we want to do it in the simplest way that equals zero, right? We have no charge. So it's kind of what these guys sort of resemble. And they also resemble it in the fact that when we write an ionic compound, it is always the positive guy first, then the negative guy. And that works for these guys as well, always positive first and then negative. So your combination that you could have is you could have a complex ion that is negatively charged, which means you would have a counter ion that is positively charged to balance out the charge. You could also have a complex ion that is positively charged, which means you would have a counter ion that is negatively charged. So very similar to ionic compounds, positive and negative, sort of balancing each other out. A complex ion, as we talked about a second ago, is basically our metal in the middle attached to one or more molecules or ion. So in this case, it is our cobalt guy. And then our ammonia here are some ligands, and also our chloride are ligands. Again, ammonia really good as it has those non-bonding electrons. Chloride being negative, going to be a really good Lewis base in this case. So our ligands are attached, and again, one unshared or unpaired electron is really a good thing, and it being polar, again, also very much helps and having that negative charge. Now, when we talk about these complex ions and the ligands that are attached, we also will talk about what is sometimes referred to as coordination number. And coordination number is the number of atoms that are directly attached to the metal. And sometimes people mess up on sort of coordination number when they look at a formula for a complex ion. They think sometimes that the subscript next to the ligands is the coordination number. And sometimes it will be the same number, but sometimes it will actually not be the same number. And it really has to do with the type of ligand that is involved. There are ligands which have one donor atom, and those are sometimes referred to as unidentate or monodentate, which means basically from one molecule of ligand, you're going to have one atom that's going to bind into the metal. And that is what water is. Basically, it's going to be the oxygen that's going to attach to the metal. So for every one water that binds in, you kind of get like one coordination number. So if you had 4 waters that attach to a metal through the oxygen, the coordination number here would be 1, 2, 3, and 4 in this case. Again, those are the 4 that are basically attached to the metal and directly attached to it. Now, there are some ligands that do attach in more than one place, but a lot of monodentate ones like water, ammonia, chloride, all the halogens, hydroxide, those are all monodentate. but there are some that can actually bind in 2 places per molecule. And one example of that is ethylendyl-diamine. In coordination chemistry, this guy is oftentimes abbreviated with an EN, and it's abbreviated both in like the name and oftentimes in the formula as well. So you'll see that EN kind of used instead of people writing out ethylendyl-diamine. And if we were to draw this, I'll give it the old college try here. We'll do like a CH2, a CH2, maybe like an NH2. This guy's got a couple of nitrogens, electrons. And so that's ethylendyl-diamine, this guy right here. And it is actually the nitrogen in this case, both nitrogens per this molecule that can attach to a metal. So if we had a metal, it's going to attach there and going to attach there. So because this is a bidentate ligand, you essentially get a 2-for-1 deal here. You get 2 attachments per molecule. So if you had something like in a formula that had a particular metal there, and maybe next to it it says En to the 2, coordination number here would actually be 4, not 2. And that's because if you had 2 of these guys, you would have one more, say, drawn underneath it. And these 2 here would attach. And although you only have 2 molecules of this ethylendyl-diamine, you actually have 4 atoms directly attached to that metal, and they are the nitrogen guys. So that's one coordination number, 2, 3, and 4 in this case. So sometimes, again, like I said, people look at a formula and go, oh, the little subscript's 2, so that's the coordination number. You just got to be aware if it is monodentate, or bidentate, or even polydentate, as we'll talk about in a second. The other sort of very common bidentate one that you come across a lot is our friend oxalate, which is C2O42-. I'll give it the second college try here. There we go. Looks something like this if you draw it up. I took chemistry once. There we go. Just once. Like that. So that is oxalate right there. And for every molecule of oxalate, it will actually attach at the single bonded oxygens, which have a formal charge of -1. So that helps it sort of give away those electrons. So every one of those will also give you kind of a 2-for-1 in terms of the coordination number as well. So those are 2 very common bidentate ones that you come across a lot. There's also ones that can bind in 3 or more sort of spots, and those are sometimes referred to as being polydentate. So something like EDTA actually can bind in 6 spots per 1 molecule, and that's why it's a really good metal chelator. Also why if you look at like ingredients and stuff, you'll sometimes see something EDTA is just used to kind of gobble up metals. Because it can bind basically 6 places per 1 molecule, it pretty much can just surround the metal and gobble it up and keep it sort of sequestered in there. Now, how do we know maybe how many ligands will attach to a particular metal? It is sort of related to sort of the charge, and things with a +1 charge typically will go probably like a coordination number 2 or 4 is very common. As typically the charge increases, the positive charge, we do sort of see the coordination number increase as well. So our +2s could do 4 or 6. Our +3s could get to sort of a coordination number of 6. So 6 ligands could attach to it. And gold, though, gold 3 will only do sort of 4. And you can kind of think of the general trend of that is sort of what we were talking about as well. Obviously, the larger the positive charge, the more sort of electron deficient it is. So the more sort of ligands that could share electrons, more room for those guys to basically share electrons, which is why they could kind of pack on some more ligands than maybe something with a smaller charge. Looks like I drew it right, so that's good. All right. I did not attempt to draw EDTA, which is this guy, ethylendyl-diamine tetraacetic acid. That'll be like the extra credit spell it later on. This is 1 place where it can attach, 2 places, 3 places, 4 places, 5 places, and 6 places. So again, as you can see, an EDTA molecule could pretty much gobble up a metal and kind of keep it there and sort of isolate it. And again, that's why I sometimes refer to as chelating agents. So here's a table, and you have a similar one in your book. Maybe we'll come back there. Some common monodentate ones, as I mentioned, water, ammonia, cyanide, thiocyanate, hydroxide, nitrite, and all those halogens, fluorine, chlorine, bromine, are good monodentates. There's our oxalate and our ethylendyl-diamine. This is diene, which has actually 3 of those nitrogens. So at each of those nitrogens, again, they can basically bind to that metal in 3 places per one. And again, as we just looked at, our EDTA. All right. So let's finish up here talking about this. What is the oxidation number of the metal in the complex ion? So take a moment to figure it out. By the way, when you look at a formula, the guy in the bracket is actually the complex ion. Actually, I think we're going to lay it up there so we can use this to continue talking next time. All right, we will lay it up, I think.